happy shake, so sing it all day long.
All right, week 6, video 2. Let's go ahead and get started with this one. Today we'll be doing chapter 22, which is a whole chapter on catalysis. Okay, we'll quickly define catalysis here. We'll say it simply just means decreasing or bringing down the activation energy. The activation energy, we'll make a simple definition here too. We'll just say it's the biggest hill of an energy diagram. Keep it nice and simple. We'll draw a quick little energy diagram just to illustrate this before we get started. And then a quick little diagram here. Up and down. Okay, so this right here is the size of that hill. Okay, that's the EA, the activation energy. There's 2 ways to decrease this. You could bring the top of the hill down or the bottom of the hill up, right? So the top of the hill is called the transition state. So when I say bring the top of the hill down, we're really saying we can stabilize the transition state. Because when you decrease energy, when you bring it down, you're stabilizing. Okay, so one way we can catalyze is stabilize the transition state, or we could bring the bottom of the hill up. The bottom of the hill is called the reactant. So we could say we could destabilize the reactant. So we could stabilize the transition state, bring the top of the hill down, or we could destabilize the reactant, bring the bottom of the hill up. And the third option is we can change the mechanism entirely, which is a completely different way of doing the entire reaction. Okay, so let's kind of color code this and track this onto our energy diagram. So blue here will be stabilizing the transition state. So I'm going to draw a version of that. Notice I kept everything the same. I just dropped the top of the hill. Okay, we'll make green here destabilizing the reactant, and we'll draw a hill for that. So in this one, I'll do a small reaction that brings my reactant up a little bit, and then we'll go to the same size of the hill, at least the peak, and we'll finish off there. And now the activation energy has still been decreased if you look at the comparisons there. Okay, and then lastly, we could say we can change the mechanism entirely. We'll do that in orange. And so I could add 2 steps here that look nothing like the original white one. This orange one's completely different, but it does have smaller hills, so its activation energy is lower, so it is indeed a form of catalysis. Okay, let's go ahead and take a look at the multiple types of catalysis that can accomplish one of these 3 things, the blue, the green, or the orange paths. Okay, so there's generally 4 types of catalysis. I'll write them up over here. The first one is an acid catalyst. We also have the inverse of that, which is the base. You could also use a nucleophile as a catalyst. And lastly, you could use a metal. Now, acids and bases have 2 subcategories. You could have a specific acid catalyst, or you could have a general acid catalyst. So I'm gonna write both of them here. Same thing for the base. You could have general or specific base catalysts. So these are gonna be the main types of catalysts we'll be going over in this chapter. We're gonna go ahead and start with acid catalysts. And remember, acid catalysts, like base catalysts, they have 2 types, general and specific. So we'll be going over that now. Acid catalyst can be simply defined as catalysis via donating a proton. That's the definition of an acid. No surprises there. Okay, so here we have the 2 types of acid catalyst, specific and general. So I'll write those up and we'll talk about features of both. First, the specific catalysis is 2 steps, where general is only 1 step. Now, the specific catalysis is 2 steps because it has a specific separate step to do what it's doing. In this case, acids donate protons. So there's a specific separate step to donate the proton. Whereas in general catalysis, as I'm writing here, everything happens all at once. So that's the main difference, 1 step versus 2 steps. Let's take a look at an example of a specific catalyst in action. So here I'm going to draw carbonyl to illustrate this, and we'll use hydronium as our acid catalysts. So now I'll just draw hydronium here, H3O plus, 1 lone pair. And you've probably done this before, probably remember from 109B, but the oxygen's lone pair grabs the proton, That puts an OH plus up top, which makes the electrophile more electrophilic, so that a nucleophile, in this case water, can attack. Okay. And so notice this is specific acid catalysts, because look, I have indeed taken 2 steps here. I'm drawing the final product here. It's going to be a hydrate. But notice how this did indeed take 2 steps. Okay, there was first this acid protonation, proton transfer, specific separate step. Okay, so specific separate protonation step. And then afterwards, you had the addition to the carbonyl step. Okay, so 2 steps. Let's look at general catalysis, general acid catalysis, to be more specific here. Maybe I shouldn't use the word specific. But anyways, general catalysis is going to be the same thing. Same exact thing. We're going to do the same mechanism, but everything's going to happen at once. So I'm going to draw both the nucleophile and the catalyst, and we're going to do everything at once in one step. We're going to protonate and attack all at once. And so then we get the same product, right? And we're pushing the same arrows. It's just we're taking less steps to do it. So now I'm going to draw the same product I did earlier. It's just a protonated hydrate. Boom, there you go. Okay, and this is one step. You both do a proton transfer and an addition all at once. Everything is happening at once. Okay. Cool. Let's look at some energy diagrams now. Tie these into some diagrams. So I'll draw 2 here, one specific, one for general. Now specific was 2 steps, right? So I gotta have 2 hills. Okay, we did a fast step and then a slow step. So the fast step will have a small hill and slow steps have big hills. But 2 hills, right? Because it's 2 steps. So I'm gonna draw a small, quick, fast protonation step and then a really big, slow addition step. And that would be the energy diagram of this reaction. Let's go ahead and scroll up. Which one of these that we started with does this remind you of? To me, it reminds me of the green one, right? We have destabilized the reactant and we did it in 2 steps. So that's one way we catalyzed the reaction. We brought the bottom of the hill up, decreasing the activation energy. Okay, and again, for review, that was quickly specific acid catalysts. Okay, let's look at general acid catalysis. Since it's only 1 step, it's only going to be 1 hill. Now, in comparison, I'm going to draw the white one here as the uncatalyzed version. So I'll write 1 uncatalyzed, white uncatalyzed, and then yellow is the general acid catalysis version. It's just 1 hill, just like our original version, but that hill is smaller than the white hill. Okay, so we stabilize our transition state in this one. Cool, let's look at base catalysis next. Okay, base catalysis is very simple. It's very similar to acid catalysis. Now, this is going to be catalysis via taking a proton because that's a definition of a base, whereas the definition of an acid earlier was catalysis via donating a proton. Anyways, very similar, just the inverse as you would expect. Now, base catalysis, like specific catalysis, base catalysis, like acid catalysis, is also separated into specific and general. In fact, it means the same thing. Specific is 2 steps long, whereas general is 1 step long. And specific has its own specific deprotonating step. In general, everything's happening at once, just like everything was for acid catalysis. Okay, so it's very, very similar. If you can do one, you can do the other. But real quick, let's dive into some examples here just to see the specific base catalysis at work. I'll use the same example Gaynor did in one of his videos, where he showed the collapse of a tetrahedral via a base catalyst. So first, we're going to pull off this proton of this oxygen, and then we're going to use the O- to collapse the tetrahedral. Okay, and we're going to do this in 2 separate steps because this is the specific version. So we need a specific separate deprotonation step. Okay, so this is our second step here, collapsing the tetrahedral and creating the carbonyl. We took 2 steps to do this as expected because this was specific. Now, in the general base catalysis, we're only going to do it in 1 step. We're going to do the same thing. We're going to deprotonate using hydroxide, but we're just going to do everything at once. We're going to collapse the tetrahedral at the same time and kick off our leaving group at the same time, forming the same product, this carbonyl, but all in 1 step here instead of 2 steps. Okay. Cool. So specific, we have specific steps, like a specific deprotonating step or a specific protonating step if you're doing base versus acid. Let's draw some energy diagrams now. Okay. So for the specific step, we're going to have for the specific diagram, we're going to have two hills because we need two steps. And for general, we're just going to have one hill, just like what we did before. Okay. Very, very similar again. The only difference here is we're switching from an acid to a base, as expected. Okay. Lastly, let's look at nucleophilic catalysis here. This one's a little bit weird, but we can think about it of an analogy that'll hopefully simplify the concept. Okay, nucleophilic catalysis is weird because it's going to completely change the mechanism. So let's look at an uncatalyzed version first. Here we have hydroxide, and it's going to react with ethyl chloride here. And we're going to do this it's going to react via an SN2 reaction. So we're going to have the hydroxide. We're going to have its lone pair, one of its lone pairs. Let me draw its lone pairs in real quick. It's going to attack and kick off the leaving group, which is chlorine, right? This is just SN2. Okay, it's happening in one step here. Okay, but what if before we did this, before the hydroxide attacked, we had a better leaving group on there? So something that was bigger than chlorine. Like bromine is bigger and iodine is definitely bigger. So what if in the catalyzed version, we took an extra step, but that extra step was something that put a better leaving group on there and made the second step faster. Okay, so this is bigger. So it's going to be a better leaving group. I'll write that down here. So here is this separate step that's not even part of the reaction, but it puts this better, bigger iodine on there. Then when we do the actual SN2 reaction we wanted to do earlier, this step would be faster. So we are taking extra steps in the nucleophilic catalysts, but the end result is better. It's faster. Okay, so I'm going to write here more steps, but it's still faster, which may seem counterintuitive, but we can think of an analogy. Imagine walking all the way to, let's say, New York City. It would take you forever. But what if you walked to only your car, and then you drove to the airport, and then you flew to New York City? That's way more steps. It's 3 steps versus 1 step, but it's much, much faster, right? So you could take more steps and still be faster. Still definitely logically sound. Okay, and that's how nucleophilic catalysis works. Just to wrap this up, let's go back up to here. This was the orange stuff, right? And so if you're trying to look at a nucleophilic catalyst on an energy diagram, I'll do it in purple here. This white is the uncatalyzed version, right? And this orange that's now turning purple is the nucleophilic catalysis version, a completely different mechanism. It's got 2 steps. It has 2 hills instead of 1. So it's very, very different, but still those hills individually are small. The size of the biggest hill for the nucleophilic catalyst is still smaller than the size of the biggest hill of the uncatalyzed version, right? So it's still been catalyzed by definition. Its activation energy has decreased. Okay, so that's a good intro for chapter 22 and catalysis in general. We'll go ahead and wrap this up there, and I'll see you guys in the next one.